study about the transient response specifications. As we know that the second order control system, we have studied the time response when the input is a unit step function, and we have studied four cases for that depending upon the value of del, the system can be underdamped, undamped, critically damped, or overdamped. Now if we analyze the transient response of a second order control system for the underdamped condition, then we will see that its values, that the output response, it depends upon the values of del and omega. Okay, so these transient response specifications, that the transient response so this transient response, it is depending upon the value of del, that is the damping ratio, and omega n is the natural frequency. Okay, and this transient response, we are considering the case of underdamped system. For underdamped system, the del is less than 1. So if we plot the output response of this underdamped system, it was like so this was the output response of an underdamped system. Now, if we see that there are some specifications or there are some parameters which define these second order control system or the underdamped second order control system. So let us see that what are these specifications. First, we have this as the delay time, that is TD. Delay time is represented by TD, and then we have this as our rise time, that is TR. Then we have this time as our peak time, that is TP. And then we have this as our settling time, TS. So we have these four times. First is the delay time, second is rise time, third is peak time, and fourth is settling time. And then we have this difference between this is our first P1, this is P2, and this is P3. Okay, and this is our D. This time this difference between one, that is, this is our 100% that are desired output, okay, but the above this desired output, whatever peak we are getting, it is the maximum overshoot. It is called maximum overshoot. So these are, we are graphically representing the transient response specifications. After it, we will study one by one all these specifications, that what are their definitions and how we can calculate these specifications. Again, writing it, we are having this TD is the delay time, TR is the rise time, TP is the peak time, and TS is the settling time. Okay, let us study these specifications one by one. First, we will start with the delay time. Delay time is the time required for the system to reach 50% of its final value. That means it is the time required for the response to reach 50%, that is half of its final value. That means if the final value is 1, then when the system has achieved its value as 0.5, and the time taken for the system to reach this 0.5 value, it is called the delay time. So if we see on the graph of this transient response specifications, you can see that this is our full, this is our desired output, that is our final value which we want, that is 1, and this is our 50%, which when we have achieved this, it is called the delay time. Okay, so delay time, it can be calculated by using the formula. Delay time, it is represented by TD equals to, so this is the formula by which we can calculate the delay time. Here, this del is the damping ratio and omega n is the natural frequency. TD, it is delay time. Okay, now the next transient response specification is rise time. Rise time is defined as so rise time, it is the time needed for the output to be equal to the input for the first time. That is, the input, you can see in the graph that it is equal to D. So this input D, when the output becomes equal to the input, then that time that it has required or the system has needed to achieve that input, that is called the rise time. Okay, and it is for the first time in the first attempt, same as that of the delay time case. So now let's derive the expression for this rise time. So if we want to derive the expression, we have to keep this output to be equal to the input, and here the input is 1. So let's derive the expression for this rise time. So the output equation, that is the output response for a second order control system, is given by so this is the output response, and to calculate the rise time, rise time is denoted as TR. Okay, so we will put this output response equals to 1, because when the output is equals to the input, that time is called the rise time, and here the input is 1. So because we are using the input signal as the unit step function, so input is 1, so putting this CT as 1, here we will have 1 minus okay. Now if we shift this 1 minus 1, it will be 0, and this E, it will come to the left hand side, and this 1, it will goes to the right hand side. So this whole expression will be equals to 0. So 0, it will be equals to E raised to the power minus del omega n t upon under root of 1 minus del square sine. Okay, so this whole term is equals to 0. Now if we see this term e raised to the power minus del omega n t, now because we are calculating the rise time and we are putting ct equals to 1, so we can change this t into tr. Okay, so this is tr. Now these, the multiplication of these two terms, it is equals to 0, so one of these terms should be equal to 0 to make the whole product as 0. Now if we analyze this value, that is e raised to the power minus del omega n tr upon under root of 1 minus del square, that cannot be equals to 0. So this e raised to the power minus omega n del tr upon under root of 1 minus del square, it cannot be equals to 0. So this remaining term sine omega n under root of 1 minus del square, it has to be equals to 0, so that the product of these two terms come out to be 0. Okay, so let's when this value of sine will be equal to 0, that is when the value of sine theta is equals to 0, when theta is equals to pi. Okay, so sine theta, it is 0 when theta is equals to pi, so this term, that is theta, it has to be equals to pi. So omega n under root of 1 minus del square, equate this to pi. So we will get omega n pi minus phi, shifting this phi to the right hand side. Now we have to calculate the rise time TR. So TR will be equals to pi minus phi upon omega n. Okay. Now we know that this omega n under root of 1 minus del square, it is equal to omega d, that is the damping frequency. So we can write this formula as pi minus phi upon omega d. So this is one of the formula for calculating the rise time. This is also a formula for calculating the rise time we have when we know the phi and omega d. Again here we can put the value of phi also. We know that phi is equals to tan inverse under root of 1 minus del square by del. Okay. So when we calculate this pi minus phi, that is TR equals to pi minus tan inverse under root of 1 minus del square by del divided by omega n under root of 1 minus del square. So this pi minus tan inverse theta, it will become tan inverse of under root of 1 minus del square upon minus del. So pi minus tan inverse, it will get convert into tan inverse under root of 1 minus del square upon minus del divided by omega n under root of 1 minus del square. So this is another formula for calculating the rise time. Okay, so these are the three formulas by which we can calculate the rise time. First is pi minus phi upon omega n under root of 1 minus del square. When we know the value of phi and omega n natural frequency and del, that is damping ratio. If we know the damping frequency, then we can use this formula pi minus phi upon omega d. And if we know the value of only the natural frequency and del, then we can use this formula. Okay, so in this way we can calculate the rise time. Now the next specification of the second order of the transient response of the second order control system is peak time. Okay, and peak time, it is represented as TP. Now this peak time, it is defined as so peak time, it is defined as the time required to reach the peak value of the step response. So peak time, it is the time required to reach the peak value, that is first peak. Whenever we obtain the first peak, so the time required to reach the peak value is now called the peak time. So let us calculate how we can calculate this peak time. Let's derive the expression for it. So this peak time, it is represented by TP, and we know that the output equation or the output response is, we have CT equals to 1 minus just remember that we are calculating all these transient response specifications when we have applied step input to a second order control system, and we are considering the case of underdamped system. Okay, so we have written the equation for the output response, and now to calculate this peak time, we have to put the derivative of this output response, that is dCt by dt. the derivative of the output response with respect to time equals to 0. Okay, so when we put this derivative equals to 0, we can calculate the peak time. So let us obtain the derivative of this output response. So dct by dt, first we have the derivative of 1, it will be 0. Then we have the derivative of this. Okay, so when we calculate it, that is dct by dt, it has to be equals to 0. So we are calculating its derivative, that is d by dt of 1 minus. So we have to calculate the derivative of this whole expression, and we have to put it equals to 0. So the derivative of 1, it is 0, and then we have this minus sign. Okay, and we have this multiplication of two terms. So consider this first term as u and this second term as v. So we have the formula that if we want to calculate the derivative of two terms which are in product, that is uv, then their differentiation will be given by v du by dt plus u dv by dt. Okay, so this is the differentiation formula which we are going to use here, because here also we are having the product of two terms. So let us first calculate the derivative of this u and then keep this v as it is. Okay, so we have dct by dt equals to, the derivative of this will be, minus sign will come outside, so this minus minus it will become plus, and then we have del omega nt, so its derivative will be del omega n. So del omega n, and this term it will remain as it is, that is e raised to the power minus del omega nt. Upon here it is also a constant 1 minus del square, so it will also remain as it is, and this is v, so we have to put v as it is. Let us again explain me this derivative of u term, it will be, this is a constant, so it will come as it is, then derivative of e raised to the power minus del omega nt will be same as it is, and then this del omega nt will be del omega n. Now we have the derivative of this second term, that is now we will calculate derivative of this. Okay, minus sign will be there, then we have e raised to the power minus del omega nt as it is, u we have to put it, and sine theta, its derivative will be cos theta. Okay, so cos omega dt plus phi. Then we have to calculate the derivative of this theta, so its derivative will be omega d. Okay, omega dt will be omega d, and phi it is a constant, so its derivative will be 0. So omega d it will come in here. Okay, so we will multiply this with omega d, and this whole expression we have to put it equals to 0. Now, if you see in both these terms, we have e raised to the power minus del omega nt upon under root of 1 minus del square as common. So, let's take it out. We have inside we will be left with del omega n sine omega dt plus phi. Here we are left with minus this omega d and cos omega dt plus phi. Okay, and this whole term it is equals to 0. So if we shift this to the right hand side, it will become 0. Okay, and then we are left with only the inside bracket terms. So let's write it. We have del omega n okay. Now we know that this omega d, it is equals to omega n under root of 1 minus del square. Okay, so if we put the value of this omega d here, we will get del omega n sine, we have here omega n under root of 1 minus del square cos omega d t plus phi equals to 0. Now here taking this omega n as common, taking del omega n as common, we are left with only sine omega dt plus phi, and inside omega n has been taken as common and del it is not present here, so we will divide it by del. So that if we when we multiply del and del, they will be cancelled out and we are left with again omega n under root of 1 minus del square. This cos term will be written as it is and this is equals to 0. Now if we shift this del omega n to the right hand side, it will become 0. So we are left with the inside bracket terms only. Now if we know that this sine, this under root of 1 minus del square, it is equals to sine phi, and del it is equals to cos phi. Okay. So substituting its value here, we will get sine minus under root is sine phi and del is cos phi. Okay. As we are calculating the peak time, so this t it has been changed to tp. Okay. So everywhere write it as tp. Now, if you shift it on this side, we will get sine omega dt tp plus phi cos phi minus sine phi cos omega d tp plus phi equals to 0. Now, this term, it has been converted into the formula sine A cos B minus sine B cos A. Okay. So this has converted into the formula sine A cos B minus sine B cos A. So it will come out to be, it will be equal to sine A minus B. So it will be sine A minus B means omega d Tp plus phi minus phi equals to 0. Okay. So this phi and phi, they will be cancelled out, plus minus. So we are left with sine omega d Tp equals to 0. So this sine theta, it is equals to 0 when theta is equals to pi. Okay, that means this omega d Tp, it is equals to pi. So putting omega d Tp equals to pi. Now from here you can calculate the value of the peak time Tp as pi upon omega d. So this is the formula with the help of which we can calculate the peak time. Tp is the peak time and omega d is the damping frequency. Omega d, it is equals to omega n under root of 1 minus del square. So if you are not given in the question that damping frequency, instead of it, if you are given natural frequency and the damping ratio, then you can also calculate the peak time. Okay, so another formula will become Tp pi upon omega n under root of 1 minus del square. Okay, so this is how we can calculate the peak time. Now the next is specification, that is the fourth specification of a control system is maximum overshoot. This maximum overshoot, it is represented by or denoted by M, and in the subscript we have P. So this is maximum overshoot, and it is defined as the maximum positive deviation the maximum positive deviation of the output with respect to its desired value. So that is called the maximum overshoot. Suppose here we are using the step input, so our desired value will be 1, and above 1, whatever peak we are obtaining, that maximum amplitude, that is called the maximum overshoot. Okay, so the formula for this maximum overshoot, it is given by percentage MP, that is percentage of the maximum overshoot. It is given by CTP, that is the output response when we are having the peak time. That is putting the value of the peak time in the output response equation, then we will get CTP, and minus 1 upon 1 into 100. 1, because our desired value here we are having the step input, so we have put here 1. Okay, so CTP minus 1, that is our desired input, divided by the desired input. So this is the percentage overshoot, where CTP, it is the time response at peak time. Okay, so let's calculate the formula for the maximum overshoot. First we will calculate CTP. Okay, so CTP, we have to put the value of T as TP, and TP we have already calculated that it is pi upon omega n under root of 1 minus del square. So putting this T as TP, we will get the output response was del omega n TP upon okay, so this is the output response equation for at the peak point. Now putting value of TP, 1 minus e raised to the power minus del omega n. TP is pi upon omega n under root of 1 minus del square divided by 1 minus del square. And here we have sine okay. So this omega n, they will be cancelled out, and this whole term omega n under root of 1 minus del square, and this will be cancelled out. So we are left with CTP equals to 1 minus Okay, so we are left with this term. Now, this sine pi plus theta, it will be equals to minus sine theta. So here we are having sine pi plus phi, so it will be equals to minus sine phi. This minus sign and minus sign, it will become plus. So we will have CTP equals to 1 plus e raised to the power okay. Now this sine phi, it is equals to under root of 1 minus del square. So putting its value here, we will have 1 plus this under root 1 minus del square and this, they will be cancelled out. So we are left with only this 1 plus e raised to the power minus del pi upon under root of 1 minus del square. So we have calculated the output response at the peak time. Okay. Now putting this value in the formula for the maximum overshoot, that we were having as CTP minus 1 upon 1 into 100. So putting the value of CTP, it is 1 plus minus 1 upon 1 into 100. So this maximum overshoot, it will be equals to 1 and 1, they will be cancelled. So we are having e raised to the power minus del pi into 100. So this is the expression for the maximum overshoot. Okay, we can use this formula whenever we want to calculate the maximum overshoot for a system. Now if we plot this maximum overshoot, then its graph will be like, because it is a decreasing exponential. Okay, so decreasing exponential, this will be percentage MP and this is 100%. So because it is a decreasing exponential, so it will come like this, and here we will have, it will have the value as 1, and this is del. We are plotting the maximum overshoot with respect to the damping ratio. Okay, that is, it is a graph of MP versus the del, that is maximum overshoot versus the damping ratio. So this was about the maximum overshoot. Now the next specification is settling time, and this is represented as TS. So settling time, it is defined as the time So settling time, it is defined as the time required or taken for the output to reach and remain within a zone of tolerance band, and this tolerance band can be 2% and 5% of its final value. That is 2% of the final value and 5% of the final value. So it is the time taken by the output to remain in this zone. That is for how much time it is in that tolerance band. That is called the settling time. So the settling time for a second order control system, it is approximated as 4 times the time constant. That is, time constant is t, so it will be 4 times the time constant, that is 4t, for the 2% tolerance band. So for the second order control system, the settling time is approximated as 4 times the time constant, that is 40, for the 2% tolerance band. That means we are having this TS, that is the settling time, it is equals to 4 time of the time constant, and time constant is given by 1 upon del omega n. So this is 4 times the time constant for the 2% tolerance band. And we have 5% tolerance band also. So for 5% we have 3 times the time constant for 5% band. So if we want to calculate the settling time for the 2% tolerance band, we will use this formula, and if we want to calculate for the 5% tolerance band, we will use this formula. Now let's calculate that how we are getting this formula. We know that the settling time, that is for this 2% tolerance band. So in 2% tolerance band, the time when the output become 98% of its final value and remains within the range of plus minus 2%. Okay, that is called it is called the settling time. So whenever you have 2% tolerance band, it means that the output has become 98% of its final value, and it will remain within that value, it will remain fixed at that value within the range of plus minus 2%. Okay, so we will equate the output equation to 98% value, then we will get the settling time. Okay, so this CT at 2% band settling time, it is what? 98%. 98%. So it means that it is 0.98. Okay, so equating this 0.98 to the output equation, that is CT, and in CT we have 1 minus e raised to the power minus del omega n t. So this t will now become ts, that is the settling time, and neglect all the other terms in the output equation. So we are left with only this 1 minus e raised to the power minus del omega n ts, neglect other terms. Now if we shift this to this side, this minus sign will become positive, and it is equals to 1 minus 0.98, that is 0.02. Now if we take logarithm on both sides, then it will be equals to minus del omega n ts, and it is equals to ln 0.02. Okay, that is we are taking the natural log on both sides. Now value of this logarithm is minus 3.912, and here we are having minus del omega and ts. So this minus and minus sign, they will be cancelled out and we are left with this. So we can calculate the settling time as 3.912 divided by the del omega n, and this can be approximately written as 4 divided by del omega n. That is, for the settling time for 2% tolerance band, it is 4 times the time constant, and in this way we can calculate the settling time for 5% tolerance band also. So this was all about the settling time, and we have here discussed all the transient response specifications. First was our peak time, delay time, rise time, maximum overshoot, and settling time. So these are the 5 main important transient response specifications. Whenever you get the questions on to calculate these specifications, just use the formulas and put the values of all the variables like damping ratio, natural frequency, damping frequency. So you will get the transient response specifications values for it. I hope this video is clear to you. Thank you.